All right, good morning, everybody. Thanks for coming. We just got a couple of stragglers coming in, so we'll just wait for those guys. And yeah, so it's nice to be here. I mean, excuse me. So yeah, I've been running infrastructure engineering at Verizon Labs for the last 5 years or so. And today I'm going to be talking to you about this thing we built called Nelson. So it's an open source system now, or thankfully now it is. And it's a sort of kind of meta orchestrator. Like it's a system that orchestrates schedulers in multiple data centers. So, and specifically, the thing I'm going to be talking to you about today is how Nelson is built on a set of theoretical foundations and actually has some principled basis. And I'll be covering these topics and how I actually applied those to sort of what is essentially a very unprincipled domain of deployment. So when I was sort of preparing this talk, I got to this thinking about this concept of rigor. And the dictionary defines it as extremely thorough, exhaustive, or accurate. And in general, I kind of was sort of reflecting on, is this a word that we can use in good faith to describe software? And I think it's sort of fairly, like, broadly speaking, like, there have been some amazing things, right? Like NASA run a rover on another planet millions of miles away. There are doctors that do medical procedures inside people's beating hearts. Like, there's some amazing software. And then, then there's like pretty much everything else. And it just, like, I kind of was looking at these and thinking, why do we find these funny? Like, we should be ashamed of ourselves for some of the things. And the fact is it's funny because we all do it. And we all know that this is the case. And so, when I was preparing this talk, thanks to Runo, it's pointed me in direction of this quote, and I think this is really very true. Pragmatism is the opposition to principle on principle, and so, yeah. Anyway, so getting back to rigorous systems, if we think about what a rigorous system would be like, theory is a foundation. So category theory, combinatorics, set theory, lots of other different types of theory. So things that are based in math by and large. And I think we don't sort of typically approach software like this, and for whatever reason, I'm not going to go into the reasons why people don't do that. But I think we all know is that for some reasons it's familiarity, some reasons it's I guess scary names, whatever it happens to be. I guess yeah, we largely don't do it. But to build rigorous systems, we need to do it. So. I think, just broadly speaking, there are some interesting trends in industry that sort of this idea of building principled systems and sort of formally verifying systems is becoming more popular. Even some popular systems like Amazon S3, among others, they even have like TLA plus specification models now. And this is kind of promising, to see more of this stuff in commercial software. And I think a lot of the time, if we build systems based on discrete principles and based on sort of these otherwise principled or theoretical foundations, we end up with sort of more sane software, which essentially means less 2 AM pagerduty. So I've got some completely unscientific graphs I'm going to use to illustrate my point. So please sort of bear with me here and ignore the fact that the lines don't go to 0, 0. Which was a question I got last time I used this chart. So. Yes, needless to say. So I think there are sort of these two curves, like sort of principled versus pragmatic curve, and I think over time we end up in a situation where if we have a sort of pragmatic approach to things, the sort of pain over time is like significant because we end up with these sort of relatively sort of ball of mud pieces of software that we iterated quickly, we got to market quickly, things were all good until about halfway along the chart, and then suddenly it sort of our pace slows sort of exponentially, and so. On the other hand, I think rigorous systems are like, you have to take this principled approach. So there is kind of a degree of like, pain perhaps maybe the incorrect vertical axis for this, but there's a great deal of thinking that has to go in to begin with. But your over time maintenance and cost of using and maintaining that system, it's all good. And so I think that these systems or these approaches are kind of they can both work, but only one really leads to kind of a more consistent view over time. And I think sort of on a probability distribution, the principal approach is sort of more likely to enable more people to ship these rigorous systems. And I think the sort of pragmatic approach over time becomes like a sort of paralysis for business, sort of restricting their ability to diversify or change their own software. And this is a discrete problem. So I guess I'd like to propose that if we build software based on principles, then we have it's easier to refactor, easier to change, easier to improve, and over time our sort of bear in mind that sort of 80 or 90% of our time is spent maintaining software, not writing greenfield software. So anyway, on to the point in hand. So we're going to be talking about deployment today, which is sort of by and large the sort of antithesis of rigor. We largely use bash scripts, bandages, Python. It's basically a ghetto of software development. It's the complete opposite of rigor. I mean, how many people here have a deploy pipeline based on Jenkins? Okay, got some brave souls who actually raised their hands. I'm going to assume everybody else is so ashamed of what they have they don't want to raise their hand no matter whatever question I ask. So we've all been there, right? Funnily enough, whenever I talk about this, I like to talk about that stuff in the third person, like it wasn't me who did that, but like I've also done that, which is how I know not to do that. So I feel your pain and share your shame. So So what is our problem statement? So the thing we're trying to solve here is that provisioning applications is sort of by and large still too slow, whether or not you're in bare metal or cloud. The story I often tell is 5 years ago it took us 2 weeks from code complete to deploy, which is, 2 weeks is forever, right? So then I got the bee under my bonnet about 4 years ago and decided, hey, I'm going to rewrite this, and so I rewrote that system and changed a bunch of processes and got it down to about 20 to 40 minutes in the sort of average case. And today it's about a minute. So sort of this kind of improvement over time. Secondly, I think sort of runtime traffic control systems are pretty medieval. Like people will often sort of tell you about their canary deployments and how they take a machine and then it's 2 machines out of 10 or whatever they're doing, or 10 machines out of 100, whatever it happens to be. I don't want my operational decisions to be to impact my Right now, every machine we run is pretty massive. It's like half terabyte of RAM with 64 cores or more. So it's I don't want that to be my unit of work, my unit of composition for these experiments that I want to run. So we need fine-grained traffic control systems, and I don't want to couple our CI and CD systems. So I don't want any sort of monolithic operation. And whatever I do, I want to make sure that the system is not brittle. The vast majority of deployment systems are exceedingly brittle. And sort of even if people do implement these sort of monolithic systems, often on Jenkins with post job after post job after post job, many teams sort of become ignorant of the side effects. It's like if you were deploying once a week, and hey, now you're deploying 100 times a day, it's like, well, you've got more artifacts. Suddenly you're producing terabytes of artifacts a week. You're producing all sorts of builds and all the other artifacts and metadata that's sort of associated with all this stuff. So your sort of success becomes a problem, and it's a very interesting kind of a set of side effects that occur. So. As mentioned, with all good systems, you need to build these things multiple times before you get it right. So this is my third or fourth time of doing this. So I hope it's right for some definition of right. So sort of lessons I've had to date are that you need to automate every single part of the system. Any pieces you don't automate either get encoded into your organizational folklore or simply become a crutch for sort of automation avoidance. There's no testing of distributed systems locally. Yes, even if you use Docker, you simply can't predict all the things that will go wrong, scaling issues, emergent properties in systems. Vast majority of large distributed systems have data-borne issues, so you're not going to detect them anyway. You need uniformity, and whatever you do, there will be these beautiful snowflakes, and we can talk a little bit later about how we can handle those. But last but not least, and this is something I'm going to be sort of spending some time talking about later, is that you need automated lifecycle management. If you are doing continuous delivery, then suddenly you don't have this issue where you've got 1 or 2 applications. You might have 1,000 applications deployed and or 1,000 versions of the same application. So it's you need to do automated cleanup. You need smart systems that know what's needed, what's not needed. How do you gracefully phase things out? So I call this automated lifecycle management. I think it's sort of an absolute requirement. So goals. We're building a new system. What are we aiming for? So we want to use the minimally powerful components. Doesn't matter whatever part of the system. In the same way we make our function sort of just do one thing and be sort of minimally powerful. I want this in my system as well. So build system just a build system, deploy system just a deploy system, so on and so on. And sort of by and large, there's this interesting relationship between. If you want to reduce the platform complexity, then you have to increase responsibility of your users. So if you basically don't trust your users, you're going to have a complex platform, period. So I think there's this sort of interesting thing with this particular piece of software, or this area of software, that like there's an interesting relationship between the sort of organizational sociology and like how the technology is. Last but not least, on this slide, I want to decentralize the process gatekeepers. There should be no build team. There should be no tickets for filing deployment, no configuration management. This is all just garbage process that like makes no actual added value. So what I want to do is I want to codify all those things, automate it, make it self-service. So just for example, like make sure that if people are checking things in, like yes, suddenly you have git blame. You know what changed when. You know who changed it. So simple things like that. It's like it's sort of partly process, partly technology. So yeah, as mentioned, I want to reduce the deployment time to 2 minutes or less. I want to support multiple DC topologies. We're going to be talking a little bit about automatic credential management and secure introduction later. And I want to encrypt absolutely everything. Encryption at rest, encryption on the wire, privacy for all the things. And there should be no manual access. So if you rely on an SSH, there's no SSH. There's also, just as a slight tangent, there's this funny thing that when you say, hey guys, we're taking away your SSH, and people are sort of like, what will I do without SSH? And then you say, well, what will you do when you log in with SSH? They'll be like, well, I go and look at the logs. And it's just people have these very rudimentary things that they believe they need this very privileged access for. And these aren't things. There are much easier and better ways to do this. So this is how we kind of arrived at Nelson. And so the first question I usually get is, why has it got a stupid name? And as you can probably tell, I'm British. And so there's this great quote, which is, desperate affairs require desperate remedies. So firstly, the fact that there's a gigantic monument to him in the middle of London is sort of, he's sort of a relatively prominent figure in British history. And secondly, like, this dude is like, yeah, this dude knows what's up. It's ops life all the way down. He knows that there's like some serious pagerduty going on. So anyway, so overview, what did we build? So unlike other systems, right? So another question we often get is like, how does Nelson compare to Kubernetes? And it's like, well, it just doesn't. Like it's not. There's like apples and oranges. Like they're like complementary tools. So think of Nelson as like if you're running Kube today or like a Nomad or Mesos or whatever you're running, you as a developer still need to make discrete choices. Like how am I doing logging? How am I shipping my logs in a way that when I've got multi-tenancy doesn't thrash the NIC? How am I doing like QoS for all my systems? How am I doing like interference management? And like if you're not sure what any of those things mean, then like yeah, that's like really normal. So and it turns out that there's this kind of there's a whole set of things that people don't know to even think for, and that's fine. That's what I want them to be like. I want them to focus on shipping their product, which is the best thing for the business. And we'll talk a little bit about operational responsibility in a minute. But Nelson is essentially providing a set of best practices for your organization as supplied by your operations team, and then all the application engineering teams get that for free. Completely based on GitHub. There's a kind soul in the community who's currently making work for GitLab, which we're pretty stoked about. But currently it works for .com or Enterprise. You can use whatever build system you want. We literally don't care. In our case, we have some state-of-the-art runtime stuff with Envoy. We'll talk a little bit about that later. And we're doing secure introduction with credentials from Vault. So every single container is completely unique. We'll talk about that as well. It can target any data center running a scheduler. So in short, Nomad, Mesos, and there's some folks in the community who are working on implementing it with Kubernetes. So that's pretty exciting. So workflow-wise, it kind of looks like this. So you put some code up to PR review, and by the way, we'll be getting to the graphs and stuff in a second. So we'll put some code up to review. Obviously, it's so awesome it gets merged. Then gets built, in our case, by Travis. Travis then does the build, produces a container, sends it to the staging registry, which is C in this case, notifies GitHub, says, hey, new release, software version 1.1.2, or whatever it happens to be. And then GitHub then notifies Nelson simply with a webhook. So in this case, we don't care what CI system you're using. It doesn't matter. Nelson will then GitHub notifies Nelson. Nelson figures out, is this something we need to do something with? And then if it is, it does any of the necessary deployment. So Nelson's sort of essentially pretty decoupled from any of the other things in the system. It only has this sort of coupling with the sort of source repository, which in this case is GitHub com or Enterprise. So in the ongoing theme of completely unscientific charts, sort of pi responsibility. So I think that there's this common misconception that ops don't care about applications, that only devs do. And I think I want to sort of dissuade or dispel that myth, because the operations people do care about your applications. It's just that we care about all the other things. So like users have concerns like, where is my application deployed? What's the health of my application? These kind of questions, which are like application-centric. Operators, on the other hand, I basically care about everything else. Like, for your given application, what is the capital utilization of hardware? What about security? What about logging? What about QoS? What about scheduling interference? Like, these are all the kind of things that operators care about. Now, they make a huge impact on your application. And so I just want to sort of say, it's all part of the same pie. Both ops and dev care about the application. Just the way that we view it is different. So from a sort of high-level perspective, Nelson has a set of features that allow us to do this. So we have this sort of very simplistic manifest file, and yes, someone is going to say, "Oh God, not another YAML file." And in part, yeah, I hear that. It's not ideal, but from a process perspective, it ends up just being like a logical definition, and we'll talk about that in a little bit, but. By having that, it allows Nelson to focus solely on like this sort of active lifecycle management. We know what's needed all the time, so we know what to clean up and what to garbage collect. Nelson also has this optional routing control plane. In certain scheduling systems, you want to use that. In other systems, you don't. So we'll talk a little bit about that too. We have comprehensive auditing, so no matter what gets done in the system, deploys, cleanups, etc. Nelson, there's an auditing function that you can go and basically talk to that and say, hey, like what happened? Why did my application get garbage collected, or whatever happened? And Nelson will sort of be able to say stuff like, yep, it was garbage collected because all the traffic was shifted to the newer version and it was superseded by 1.1.2 or something like that. So that's pretty neat. And we have this sort of extensible, with sort of different arbitrary scheduling or routing or artifact systems. And that's based on free monads and coproducts. We'll be talking about that later, which is pretty fun. So I started this talk talking about rigorous systems. And to have these sort of theoretical foundations, for Nelson, that's primarily two things, which is sort of, this idea of graphs and this idea of coproducts. So graphs, we have a very nice library called Quiver, which some of us worked on. Runar sat in the front here. I ported that from Haskell. So the FGLs from Haskell was ported to Scala, so now it's called Quiver. So we have a very nice library for this. So it allows us to model several different things. So graphs have this idea of a vertex. So a vertex is simply a vertex n with some type level L. And then we have edges, so from vertex A to vertex B. We have directed edges, and it turns out, well, they're easily modelable as well. You have an edge with a type, or a labeled edge with a type and a type for the label. So if we have many of these, we create graph. Now it turns out that there's this very nice property about graphs, which is that they're monoids. So if I'm moving too quickly, I'm sorry if people don't know what monoids are. I'm not going to go into what they are or what they're not. Yeah, please look it up. But it's a very nice property, very high level, has these function signatures in most implementations. And so this allows us to basically merge the graphs. So yes, someone will pull me up about associativity laws and stuff like that. So anyway, that's a secondary thing there. From the high-level takeaway here is that because these graphs are monoidal, we can merge them all together. Now, if we look at a sort of more applicable graph when we think about deployment, well, we always talk about our applications just like they're graphs, except that we never model them as graphs. So when I think about my application as a user, I'm like, well, I need B and C to work because I'm A. And so we can sort of logically say that A logically depends on B. And so A logically depends on C, which depends on E. So from an operational perspective, I know that, just from a human perspective, I know that, well, A sort of transitively depends on E. And so if we can make these kind of rationalizations ourselves, then why don't we just codify that into the system so the system knows about all these transitive dependencies? And so we actually already do this in our dependencies for our local build. This is exactly what Ivy or Ether or any of the other dependency management systems is doing. It's just that we just don't do that at runtime, for some bizarre reason. So if we take off the labels there, and we add some more sort of deployment-ready labels, we can say that, OK, this particular version of an application requires this other version of an application. And we can kind of build up this graph. And so the nice thing about this is that from your application's perspective, you only ever need to tell Nelson, what you depend on. So if every single person in the system, or every single agent in the system, every single service, is just telling Nelson what they depend on, then all we need to do is essentially sum all the applications and all their graphs, and we build the whole world. And so it's like you take all these little partial graphs, merge them all together, and then you know what the whole world is. And if anybody's sort of like squinting, thinking like, really, does that work? And yeah, it does. And so we can talk about some of the interesting things about, there are some details about how certain things work, but this allows us to sort of derive several useful pieces of information. So firstly, it means that like if you have different vertices on the graph that aren't connected, there's no relationship, so there's no routing. So likewise, if those vertices aren't connected, that means that system A can't talk to system X, so therefore never provision credentials for system X because it will never need it. And so it turns out that there's these sort of very interesting things that we can derive from the fact that this is a graph. And essentially just leaning into what it is already, because we do these things continually. So for example, many systems lean towards systems like like open tracing or Zipkin or something, because they don't know what they deployed, and then they look to tracing to figure out, okay, well, what are the relationships in the system? And it's like, you know what they are because we built the system. It's just that we just forgot to codify it anywhere. So instead of doing that, if we just say, hey, when you're building your system, why don't you just tell us what it is you were using, and then we can figure out many other things and make a sort of safer, more secure system. So the entire worldview falls out of this union of all these sort of discrete graphs. And there's a sort of nice sort of aspect to this, which is that the edges of the graph, which are sort of form the ingress to the system. So those things, like typically, like if anyone familiar with Kubernetes, your ingress controller is essentially the edge of the world. Likewise, your load balancer is the edge of the world. These are just different systems that allow inbound traffic to the rest of the graph. And so we use those as kind of like an anchor point for the graph, or sort of root of the graph. I'll take questions at the end, if that's OK. So I want to talk a little bit about lifecycle with this stuff. So lifecycle is something we typically end up doing. Like most companies end up doing this with like some hacky bash script or some like Python script. And once upon a time, we used to do this with Python, just a Python script too, until based on an AWS bug, it like nuked a whole part of the system because it wasn't expecting an empty array. So that was pretty much the time when we decided, hey, we should really like codify this in a more formal manner. So anyway, so this is a great tweet from one of Vogel's. He tweeted this a couple of years back. This is Amazon's system in 2008. So like many large enterprises, like this is 10 years ago nearly. Think about how more complicated their system is in all likelihood 10 years from then. This is a gigantic graph. We also have a gigantic graph. And it's like many large systems have these big graphs. And it's like, for some reason, we just never, like, we haven't looked to basically do this automatic graph pruning or handle these like automated life cycles and things and accept what we and actually codify or automate all the cleanup and associated tasks with these things. So I want to talk a little bit about the life cycle of a given application that gets deployed with Nelson, and then how we do garbage collection to try and avoid running all these things over time. So an application that's deployed with Nelson goes through a set of states. So it's basically just a small state machine that we have internally. So an application gets deployed. So in this case, it moves from pending to deploying to warming. And warming is kind of this interesting thing. By default, it's based on console. So we have these health checks. And the idea of the health checks is that an application can tell us when it's ready to receive traffic. So for example, if you have an application that boots up and it needs like 5 minutes to do a cache warm or something, then it can basically stay in the warming state and then just indicate, oh, OK, now I'm ready to receive traffic. And so we delegate that to users, and that's sort of a nice thing. But by and large, most applications get deployed, and then they move immediately to the ready state if they don't have any such warm-up things. And so over time, and it doesn't matter whether or not it's today or tomorrow or next year, the application will eventually become garbage. We'll talk about why that is in a little bit. But then there's the next state they typically move to is garbage, and obviously then they get cleaned up and become terminated. Now there's a sort of other workflow that's kind of interesting, which is this idea of deprecation. So over time, by the way, I sort of love the maintenance aspects of all this because it's something we never really address. Typically what happens is that I produce an API, then maybe a year goes by, maybe 2 years go by, whatever it is, and then I'm on version 3 of something, major version 3, and then someone else is still using the old version of my API, and I need to do some schema change or something that's some now incompatible change to the old revision. I can deprecate my system. And then at that point, it basically triggers, Nelson looks through the graph and says, who's using that old version? And then it goes and says, tells everybody, the people that were using that system, you got to upgrade. Like that thing is deprecated. And so this is sort of another nice thing that as an API producer, you now know who all your consumers are. And this is actually typically like something that most people run afoul of in large distributed systems simply because of Conway's law. Like in a large company, you end up in a system where you produce an API, and you might have 5 APIs, maybe 3 are read APIs, 2 are write APIs, whatever. And someone uses your API in a way that you are not familiar with, or they do something that you weren't expecting, essentially. And so this idea to be able to like know who your consumers are, sort of inverse traversal of the graph from your position is really useful. So yeah, so this is basically sort of the internal workflow about how Nelson decides, it sort of traverses the graph and figures out like, who's garbage basically. So there's sort of a fundamental tenet here, which is that like every single application has this sort of TTL. Like we will delete everything eventually, like period. And so it doesn't matter whether or not it's today or tomorrow or next year. At some point that thing will not be needed. And so based on this concept that like everything is running on this extended, this essentially TTL, we can just bump the TTLs to retain the application. And then if we don't want to retain it, well, we just don't bump the time. We just don't bump the expiry. And so there are a set of policies that we can use to evaluate this. But once we've, once that thing has expired, then it just gets marked as garbage, and another process will come and clean it up. And so one of the policies we have is this idea of graph pruning. And so because we know the graph, as we were talking about up to now, so in the event where the producers of system F, they roll out a new version, and that new version doesn't need the G system. So Nelson would be like, oh, well, G is basically orphaned now, so it's not being used, so that can also be cleaned up. And so when we do this, we can shift all the traffic from F1.2 to 1.3, so we can sort of seamlessly know that we moved all the traffic, no one was affected, and once that's done, the F1.2 becomes garbage and then eventually gets terminated. So that's very, very nice. Like there's not, this is sort of not common, and it's a very nice, in practice it becomes very nice because you never end up in those sort of discussions where someone's going around saying, do we really need this system anymore? And then, by the way, you've got like 100 of those systems and it's costing you like thousands of bucks a month, like, just to run those things. So it sort of does away with those things. Another common kind of workflow, typically for data science, is like, objective model comparison. So I might have like my production model, which is like 3.4, and then I've got like 4.1. I'm doing some other stuff, and I want to objectively compare and contrast those models at runtime. So it can do that too, and keep around all these different versions to allow you to iterate. Last 2 features, so on. You can see these are simple Boolean algebras essentially. So this is pluggable, and you can pretty much do whatever you would like to do there. So. We mentioned security too, so trying to stay on the theme of graphs and all the interesting things that we can sort of derive from the graph. And by and large, I think security is that thing that everybody wishes they did better because they kind of like know that they, or maybe they rely on like perimeter defense or whatever it is. But there's like many janky things that people do pertaining to security, and I would propose that those things, when you derive them from a graph, like a sort of authoritative graph about what the system should be like, the desired state of the world, you can actually sort of have a safer system. And so some of the things that we derive from this graph is this idea of deriving security policy, not proclamating it. And so typically what we sort of do, or what many security people do, is that this application should not talk to this application, or something like that, right? And like saying that is basically like useless, like because someone somewhere has to then go and implement that. And so if that policy ever changes, or there's a change in the relationships, usually that stuff doesn't get updated, and it's this bolt-on thing, like it's like an afterthought in many systems. So instead, Nelson can actually generate these policies, and based on the graph, because it knows that, oh, you used to use this one, or now use this one, okay, yeah, remove that policy. Now it's generating the actual policy that will be used to derive your credentials. So that's super useful. So you're basically getting like policy cleanup for free. Now, because we know these sort of internal and external dependencies for any given application, it means that we have an easy way to audit the system, both inside and out. It's like, oh, you need to talk to a vendor. Oh, the vendor needs credentials. OK, great. Well, they get provisioned to Vault. You also have to declare them. So otherwise, they don't get put into your security policy, so you don't get access to them. So you end up in the situation where you get a single point that knows all the things that could talk to all the things. And so you can run a simple audit. This is really, really nice. And so from a practical perspective, when containers are scheduled, like every single application instance ends up with these unique credentials. So unique certificates, unique database access, like all that stuff can be generated per container. So if you get compromised, all you need to do is blow away the container, and then you haven't lost anything because those credentials don't work anymore. So these kind of aspects of it are sort of really nice. Like if you go with this completely arbitrary, completely ephemeral, sort of security model based on the desired state of the world, you can automatically provision a lot of these things with a minimal of hassle. Now, just on top of that, like if you know that you're doing this, if you want to use a service mesh like Envoy or Linkerd or something like that, you can just do transparent MTLS for everybody because you're automatically generating the certificates, again, per container. And because you're doing it per container, you can add all the extensions and all the other things that you would want. So if you want to do like SNI or any kind of like alt name stuff for your security, depending on whatever you want to do, it's a breeze too because you're just generating it per container. Like you're generating that stuff anyways. So. Yeah, this is really cool. I know this is like high level. If anyone wants to talk about that stuff like after the fact, I'd love to. I think this is one of the really interesting parts of doing this kind of system. So I'm going to move on to another sort of component that's graph-like in Nelson, or indeed is a graph. So we have this concept of namespaces. So this is an optional part of the system. By and large, it's if you're using the control plane part of Nelson for routing, this is in play. If not, then it's not. But it's sort of a very interesting thing that we built that not many people are doing anything like. So sort of very, very high level. I'm not too sure how many people are familiar, but so we have this sort of scheduling substrate. You have a set of machines, and then you run a scheduler on top of it so that you can address all the machines, simply as a pool of resources. Pretty common. So tools like Nomad, tools like Kubernetes, tools like Mesos. These are resource managers that allow you to address this pool of resources, as a single homogeneous, available set of resources. So for example, instead of saying I need X machines, you simply say I need I need 400 gigabytes of RAM, find it on the cluster for me, I don't care where I am, these kind of things. So what we did is we basically built this sort of set of namespaces on top. And so this is a completely virtual concept. There's no, there's no physical thing here. It's simply like this virtual construct to say, okay, this pool of this pool, like not even related to the resources, but this group of things is this route. This group of things is another route. Now in this diagram, I've used dev QA prod, but like in actual fact, like these are arbitrary. Like you name them whatever you want, but it's sort of most illustrative for most people to kind of think about it in this way. Now the sort of interesting thing about these things is that the namespaces, they're also trees, which are subsets of graphs. So now the root thing, what we call the root namespace, the root of the tree in this case, let's say it's QA. Now I can define another, a sort of sub namespace under that, QA unstable, and I could even define like another one called staging, and then I could have another one specifically just for me. And so if we're doing resolution about like discovery, who do I need to talk to, there's sort of some very interesting things we can do in the sense that because I depended on a particular application, I can be like, OK, does that application exist in my namespace? So typical use cases for this are like this is a hilarious thing about most dev or QA environments. People they want to try their system, but they want to try their system with the rest of the world that doesn't change. And so when everybody wants to do that, you end up with a system that never works because like everything is unstable because everybody wants to try their thing with everything else, but everybody is doing that, so it makes the whole system unstable. And so subsequently, we realized that there's this kind of like multifaceted aspect to it, which is like what you want to do is you want to say, OK, deploy my thing, and I'm just going to deploy my thing in my special namespace, and then it's going to resolve up to see, like, OK, is the thing I'm looking for available in staging? Oh, no, it's not available in staging. Is it available in QA? Oh, yeah, it is. So then you get this like sort of multifaceted view of like, OK, I'm using my application, just the special custom one that I deployed, with the standard QA one of everything everything else. And so because these are completely arbitrary, you can have as many as you like. Every dev could have their own namespace if they wanted. It's like completely virtual. But in terms of like doing discovery and stuff, it means that people can have like these sort of sandboxes just to do whatever they want, and it's just completely it's just shared on the same cluster without any sort of concern about stepping on someone else's toes, essentially. And so if you want to deploy, even if you have a tight coupling with another system, you can even deploy that on their behalf in your namespace for some special testing. So all these things are really nice. And this works for both services, databases, any other dependency we have in a network. Sort of turns out that it's some really nice property. So in terms of discovery and routing, I think they're like pretty related concerns, but it's sort of important to understand why they're different. I think discovery is simply about taking the sort of like logical name, like accounts or software update or like users or something like that, like some kind of logical part of the system, and telling you sort of what that fully qualified name is, where specifically is it. And routing, on the other hand, is sort of telling you about how to actually make move traffic to that particular endpoint. So for example, convert it to IP port names or something like that. And there'll be various distinct revisions, all of this intercommunicating systems. And I think that's the difference between discovery and routing. So in our case, if you are using the control plane in Nelson, we have this discovery protocol, which we call the Lighthouse protocol. I'm not going to talk too much about this, so I'm going to skip forward a little bit, run a little bit tight on time, because apparently I'm slower than I had anticipated. But this is online. I totally recommend that you go and look at it. And I've done a couple of talks about this before. So anyway, long story short, there are some very nice things you can do with Nelson and its routing control plane, which is that you can say, OK, I want you to shift traffic, but I want you to shift traffic in using a power curve. So like, for example, I want to, over 50 minutes, move all my traffic using a power curve or use a logistical curve or whatever it happens to be. And so this sort of curve-based traffic shifting allows you to move traffic in a way that makes sense for you over a time that makes sense for you. If you're a front-end system and you've got 10 million customers, obviously you're not going to move that thing in 5 minutes. It's going to take a long time or much longer time to do that without causing a customer impacting outage. So anyway, yeah, this is documented online. If anybody wants to talk about it, I think this is really interesting. And doing this stuff allows us to the namespace and things allow us to do this kind of traffic shifting without impacting users. So. I've got some links at the end. Can I come to that? Thank you. Yeah. So workflow. So workflow is kind of this idea in Nelson that's like it's sort of like how the sausage is made, how we hold all the things together. And so by and large, we have this. So internally, we have like a set of executors, and this set of executors basically just pull off work on the queue, and then they execute these workflows. So the workflows, they're also this kind of graph-like system. So they do this thing, and then they do this other thing, and so on and so on. And it turns out that workflows sort of conceptually are graphs. And in other more generic scenarios, internally we do actually model these workflows, and rule engines as graphs. But in this particular case, we made a specific decision to use a discretely less powerful thing, and that less powerful thing in this case was coproducts. Because what we didn't want to do is we didn't want to fall into the same trap in Jenkins, which is where you can basically build these complicated DAGs of things and so forth. So we basically choose, once again, to use the sort of minimally powerful thing. So I had some background on coproducts and things, so I'm just going to skip through that because I'm running a little bit tight on time. But based on the audience, I think most of you are sort of familiar with coproducts. But we essentially build this algebra. We build this algebra internally, which takes all these discrete parts of the system, like how do we deal with Docker, how do we deal with the scheduler, how do we deal with all these other things, and you essentially end up with like coproducts of coproducts of coproducts of coproducts, all these discrete programs. So our program is simply a program of programs. So when we're actually building the workflow reads almost like English text in some senses. It's simply a for comprehension that says, okay, like do this thing, okay, write the policies to Vault, and then I've removed some stuff because it wouldn't fit on the slide. Does a bunch of other things, then launch it. And so it simply just says, do this, do this, do this, do this. And so by having this coproduct approach instead of doing a graph, there's no complicated DAGs, there's no complicated, people don't build logic into Nelson that would be an abuse of the system. So it's it specifically disables that kind of thing. So this is super interesting. I show this only to show that it's very straightforward. So please go and have a look. If anybody's got any questions on how that workflow subsystem works, it's really interesting. So this is definitely like a non-trivial system, right? We didn't build this thing overnight. Right now, we've got fairly tight integration on the open source version with HashiStack. Right now, there's the community are adding support for Kubernetes and Istio, which is awesome. I'm stoked to see that happening. And also good to see that even people who are using other systems recognize that they're still going to end up in these same problems where they can't clean up and they need some kind of lifecycle manager. And so, yeah. So we have several challenges. I think it's I think if you're a tiny organization, this is probably overkill, to be frank. But if you are running a scheduler or you have more than 100 nodes in your system, to the point where you're thinking about running a scheduler, like please consider like all these side effects and all the other things we've talked about that are sort of running up into that could cause you problems. So in summary. Using principled systems like Nelson, having been built on these sort of foundational concepts, they can provide some rigor to the rest of your application. And I think not having this manual housekeeping, being able to choose whatever CI you want, being able to secure deployments, all these nice things that fall out of having graph-based structures, they get you a lot and they don't cost much. So yeah, anyway. With that, thanks very much. I know I ran tight on time. There's a link here at the end, so if you're interested in the documentation, it's all online. If anybody's got any questions, I'd be more than happy to talk to you. And I've got some links in the end of the slide about other projects and stuff that are related, like the graph library I mentioned and all the other things we ported to Scala. So I'll post them online and put it on Twitter. So anyway, thank you very much for listening, and I'm sorry I ran a bit tight on time. Thanks.
And we still have time for a question or two, and give you enough time to get to the next session.
Thanks for the talk.
Mm-hmm.
You mentioned documentations at that link.
Yep.
Is there developer documentation as well? Like,
yep.
I'm not talking about like APIs. I'm talking more like kind of like what your slides have gone into the theory of it, except more in depth.
That's a good question. So we do have some stuff on there. Depending on your questions, it may or may not be there. But if there's anything that you're specifically looking for, I'd be happy to add it.
Great.
Yeah.
You said the slides will be online?
Yep, I'll post the slides right after this session.
Thank you.
Mm-hmm. Welcome.
And, one more question back.
The edge relations in your graphs that you showed on the slides were depends on, but you can think of lots of other things that I imagine must be in your system, things like trusts, A trusts B,
yeah.
A knows about B, not just depends on application version, but depends on interface version. Like,
yep.
How rich is the space of relations that you're actually working with?
Yeah, so that's a really great question. So we did have to make some choices, and so at the end of the day, you have to kind of boil down to something that people could understand. And so we did originally, our original spec of this system had a much more complicated system like the one you're talking about. And in the end, we just decided, hey, you know what? Like, the system is becoming complex. So as I was mentioning, in order to sort of reduce the platform complexity, we had to make a trade-off. And so the trade-off was, hey, the users, they have to basically follow semantic versioning, and the interface is essentially defined by the semver. So it's not ideal. Like, we tried to retrofit some stuff. Like our plan was to basically retrofit it so that the contracts for the systems themselves was basically published. Like, we made a project called Remotely. It's on GitHub, you can check it out. But like, it was an experiment, and the idea was that what we wanted to do is to basically like have compile time verification on the contracts, so that if you were publishing semver, then like you could actually see, okay, like System X upstream said that they had this contract. Did they actually have it? And we didn't get too far along with that. Currently, we basically just rely on semver and essentially continuous testing to make sure we did the right thing. But yeah, it's definitely a trade-off. So for security and stuff, we rely pretty heavily on the like depends on. We might need to talk a little bit more after it, but happy to.
Thank you. Thank you, too.
Thank you very much. I will do. Mm-hmm.